From Earth, people have watched Venus since before there were telescopes, calling it the morning star when it rises before dawn and the evening star when it hangs over sunset. Galileo's telescope in 1610 showed Venus has phases like the moon, fat gibbous, slim crescent, and that single observation helped lock in the idea that the planets go around the sun, not us. Later, when astronomers timed the rare transits of Venus across the solar disk from sites all over Earth, they used the geometry to nail down the scale of the solar system. In other words, Venus looks pretty, but it also paid the bills for celestial mechanics. Let's set the basics next to Earth so nothing floats away into abstraction. Venus is almost our twin in size, about 95% of Earth's diameter and 81% of our mass. Gravity at the surface is close to Earth's. You'd weigh just a hair less. A year on Venus is about 225 Earth days, so it orbits the Sun a little faster than we do, but the rotation is bizarre. Venus spins backward, retrograde, very slowly. One spin takes about 243 Earth days, and because the planet is moving around the Sun while it turns, the sun up to sun-up solar day on the surface is about 117 Earth days. Short year, long day, and the sun rises in the west and sets in the east. If you're keeping a calendar there, you're braver than me. Now the headline everyone remembers, the air. Earth's atmosphere is a breathable mix with a surface pressure of about 1 bar. Venus's atmosphere is a suffocating blanket, roughly 96% carbon dioxide with few percent nitrogen and a cocktail of trace gases, stacked so thick that the pressure at the surface is about 92 bars, like being a kilometer under Earth's ocean. That blanket traps heat with a vengeance. Surface temperatures hover around 465 degrees Celsius, pretty much everywhere, day and night, pole and equator. Earth has a greenhouse effect that keeps the planet comfortable. Venus has the greenhouse effect turned up to pizza stone melts. There is no cooler at night on Venus. The air is too deep and too efficient at moving heat around for big swings. The clouds, by the way, are not water clouds like Earth's. Most of the visible cloud deck, roughly 50 to 70 kilometers up, is sulfuric acid droplets in a haze of CO2 and minor gases. You don't want to fly through that without the kind of umbrella no one sells. Those cloud tops race around the planet in about 4 Earth days. That's super rotation, a giant atmospheric conveyor belt that outruns the planet's lazy spin by a factor of 60. Up high, winds are hurricane fast. Down near the surface, the winds crawl, but because the air is so dense, even a slow breeze down there shoves like a gale on Earth. If you could stand on the surface, and you can't, unless you're a Soviet Venera lander built like a stainless steel pressure cooker, you'd see a dim orange world. Sunlight does reach the ground, but it's filtered through so much atmosphere that the light feels like a permanent overcast. The sky isn't blue, it's a coppery sepia. There are no oceans, no rivers, no rain that hits the ground. The acid droplets in the clouds evaporate before they fall very far. Vega. But the harsh version, so the surface stays dry and hellishly hot. What does that surface look like? Radar mapping, because visible light can't get through the clouds, shows that most of Venus is broad volcanic plains, basaltic, dark, and relatively smooth, broken by continent-sized highlands and stitched with rift zones. Two big highland regions carry names to remember: Ishtar Terra near the north, home to Maxwell Montes, the tallest mountain on Venus, and Aphrodite Terra along the equator, a sprawling uplift carved by fractures. Scattered across the plains are thousands of volcanoes, from small shield cones to big domes and odd features you don't see on Earth. Coronae, wide, circular or oval patterns of fractures and ridges like someone pressed a hot ring into softened rock. These likely form when hot material from the mantle pushes up, warping and cracking the crust from below. You also get tesserae, complex, crisscrossed terrains that look like folded tile, ancient, deformed crust that has been squeezed and lifted. Earth's continents show off plate boundaries. Venus shows off what you get when there are no plates, a stagnant lid planet that vents heat in fits and starts, lifting and cracking the crust over broad regions rather than shoving sea floors under continents. You'll hear two simple, honest statements about Venus's timeline. The surface is young, and volcanism is part of the reason. Counting impact craters, the few that survive in that thick atmosphere, suggests the surface we see today averages hundreds of millions of years old, not billions. That implies Venus got resurfaced on a grand scale, lava plains flooding vast areas, corona reworking the crust, rifts opening and closing. Is Venus still active right now? The safest version is probably, at least in places, and we've seen hints. Some thermal hot spots up high, some suspicious changes in radar reflectivity at volcanic edifices when we look years apart, and an atmosphere that sometimes behaves as if fresh gases are burping out. We don't need to oversell it. Venus doesn't have glowing lava lakes on a tourist brochure, but the planet hasn't retired either. Under the lid, Venus should look familiar: an iron core, a rocky mantle, and a crust. The core is likely at least partly liquid, but here's the kicker: no global magnetic field like Earth's. That doesn't mean there's no interaction with the solar wind. Venus grows an induced magnetosphere when the solar wind wraps around its ionosphere. It's a magnetic bubble by force, not by dynamo. Why no dynamo? Probably a mix of slow planetary rotation and the way heat moves inside, a mantle and core that don't set up the right kind of organized churning flow to run a generator the way Earth does. In short, similar parts, different settings. Compare atmospheres cleanly for a moment, because it explains almost everything you feel on Venus. Earth's air, one bar, mostly nitrogen and oxygen, with wisps of water vapor and some carbon dioxide. It gives us blue skies, clouds, rain, a breathable mix, and a planet where heat can move but not lock in. Venus's air, 96% CO2 at 92 bars, sulfuric-acid cloud decks up high, and almost no water vapor. That combination traps heat viciously and supports odd chemistry. Lightning? Signs point to electrical activity in the clouds. Rain? Acid droplets condense and start to fall, then evaporate in the lower, hotter layers so the ground stays dry. Weather? Yes, but it's alien. Fast jets and waves in the cloud tops, slow motion pressure cooker dynamics near the ground. If Earth is a temperate kitchen, Venus is the oven on self-clean. So how did it get this way? The thumbnail story goes like this. Venus and Earth likely started with similar ingredients: rock, metal, some water, and volatiles. On Venus, being a little closer to the sun and perhaps receiving a different early bombardment and interior mixing, water never got the upper hand. With less liquid water to dissolve and lock away carbon dioxide in rocks, CO2 stayed in the air. More CO2 made the air hotter. Hotter air made it harder for water to stick around. Losing water stripped the planet of a key way to regulate climate and drive plate tectonics. Once the greenhouse really took over, the system settled into its current state, hot, thick, and stable in the worst possible sense. Earth found a long-term thermostat with oceans, weathering, and plate recycling. Venus found a long-term sauna. Despite that, Venus still connects to our sky in friendly ways. It's the brightest planet in Earth's night, often blazing at magnitude -4 or so, bright enough to cast a faint shadow under very dark skies. Because Venus orbits inside Earth's path, it shows phases. Through binoculars at greatest elongation, you'll see a tiny disk. Through a small telescope, a clean crescent or gibbous. And every so often, when the alignment is perfect, Venus transits the sun, a tiny black bead strolling across the glare. Those transits come in pairs, separated by more than a century. The last pair was 2004 and 2012, and the next is in the 22nd century. If you missed the show, welcome to astronomy. You always miss something, and there's always something else coming. Missions are how we know any of this for sure. The Soviet Venera landers, built like squat kettles, survived on the surface for minutes to a couple of hours before the heat and pressure ended the party. They sent back the only photos and in situ data we have from the ground. The Vega balloons floated in the clouds and rode the winds. Magellan, an American orbiter in the 1990s, mapped the planet with radar and showed us the plains, corona, domes, and rifts in stunning detail. Venus Express from ESA and Akatsuki from JAXA watched the atmosphere for years, measuring winds, waves, and chemistry, and snapping infrared views of the cloud tops. The next generation, NASA's DAVINCI probe and VERITAS orbiter, plus ESA's EnVision, is aimed straight at the big unknowns. How the surface and interior really work, where the active volcanoes are, what the tesserae are made of, and how the atmosphere breathes from top to bottom. Dates slide. That's space flight. The questions are steady. A few comparisons help keep the story straight. Temperature. Earth varies, but we live mostly between -50 degrees Celsius and +50 degrees Celsius. Venus sits at +465 degrees Celsius all the time. Pressure. Earth's 1 bar versus Venus's 92 bars. Water. Earth's surface covered in oceans. Venus has a trace of water vapor and not much else. Any rain you imagine is acid and evaporates before touchdown. Magnetism. Earth's global dynamo versus Venus's induced bubble. Rotation. Earth's 24 hours prograde, Venus's 117-day solar day retrograde. Tectonics. Earth's mobile plates versus Venus's stagnant lid plus rifts and coronae. Moons. Earth has one. Venus has none. That last one isn't a moral lesson, it's just orbital history. But if you're looking for the one-line contrast, here it is. Earth is a climate machine. Venus is a climate warning. There's a temptation to turn Venus into a parable. This is what happens if you add CO2. The truth is more complicated and less comforting. Venus didn't have our oceans, continents, or life to begin with. Its starting conditions and early evolution were different. Still, the physics is the physics. CO2 in large amounts traps heat, and a planet without a way to bury that carbon ends up very hot. No sermon needed. Just note the sign and keep walking. Let's finish with what you would actually see if you could ride a tough little probe down. At 70 kilometers up, bright white sulfuric acid clouds racing by in 4-day laps. At 50, still cloudy, temperatures near room temperature, pressure roughly like a cabin's, but the chemistry would dissolve your hardware. At 30, the haze thickens, the light goes amber, the temperature and pressure start to bite. At the surface, orange gloom, flat volcanic plains broken by blocky rocks and low rises. The horizon a bit closer than on Earth because the planet is smaller. The air thick enough to bend the light so the distance looks warped. No breeze to speak of, but the weight of the air sits on everything like a wet blanket you can't lift. The ground is basalt. If you could pick up a rock, it would be hot to the touch because everything is. And above you, somewhere beyond the overcast, the sun crawls the wrong way across the sky. That's Venus, dazzling from here, punishing down there, scientifically rich everywhere. It's almost our size with completely different outcomes. A planet that chose the other fork in the road and followed it all the way. When you see it blazing after sunset, it's easy to think evening star and move on. Now you know the rest. A carbon dioxide ocean of air, acid clouds tearing around the planet in 4 days. A lid of rock that lifts and cracks instead of sliding, plains poured by ancient fire, hints of heat still working below, and a clock that runs backward. If Earth is a house with a thermostat and plumbing, Venus is the same floor plan with the thermostat welded on high and the pipes full of acid. Beautiful from a distance. Up close, absolutely honest about the rules. Let's take the tour from the top of Venus's sky down to the ground. No fluff, just the parts that make your eyebrows go up. Start above the clouds. At about 70 kilometers up, the air is thin, cold, and fast. This is where the bright white sulfuric acid cloud tops race around the planet in roughly 4 Earth days. That's the famous superrotation, the atmosphere lapping the solid planet about 60 times faster than the ground turns. From orbit, you can watch long, high-gravity waves, ripples in the cloud deck hundreds of kilometers wide, marching downstream like corduroy. Over each pole, the winds coil into double-eyed vortices, a hypnotic, slowly tumbling hurricane shape big enough to swallow continents. Down here on Earth, we get jet streams and neat satellite spirals. On Venus, the whole atmosphere is basically a jet stream with a planet under it. Drop to about 50 to 60 kilometers, and you hit the maybe livable zone, livable for robots, not for you. Temperatures there hover around room temperature, and pressures are similar to a pressurized airplane cabin. That's why people float trial balloons, literally, about aerostats. Airships that could cruise at that altitude, above the worst heat and pressure, sipping data from a place where hardware doesn't melt. The catch: the clouds are sulfuric acid, and the air is almost entirely CO2 with almost no water. It's like camping in a nice breeze inside a chemistry set. Keep descending, and the light turns amber as the haze thickens. Winds slow down near the surface. You'd think that means gentle weather, but gentle is doing a lot of work. At the surface, the air is so dense that even a slow wind has the muscle of a gale on Earth. Imagine pushing your hand through soup that's hot, heavy, and slightly corrosive. Charming. Now the ground, volcanic plains as far as you can see, with occasional rises and broken, blocky rocks. Radar mapping from Magellan painted the big picture. Venus is a planet of basalt, lava, that spread into broad sheets, cut and lifted into continent-sized highlands and rifts. Without plate tectonics to build tidy ranges, the crust warps and heaves in broad regions. That's where the odd Venus-only features show up. Coronae, giant, circular or oval fracture patterns, hundreds of kilometers wide, like a hot ring pressed into softened crust. They probably form when hot mantle material wells up, domes the surface, and then the crust sags and cracks as the heat bleeds away. Tesserae, gnarly, crisscrossed uplands with multiple sets of ridges and troughs. Think tile that's been folded and refolded. They're some of the oldest surfaces on the planet and a big target for new missions because their composition could tell us whether Venus ever had patches of crust that behaved a little like continents. Pancake domes and lava channels, coronae, wide, flat volcanic domes and sinuous channels that run for hundreds of kilometers. Earth has lava tubes and channels, but Venus drew them longer and smoother, probably thanks to different lava chemistry and that crushing air. Is any of this active today? The cautious answer is very likely in places. We've seen hints, thermal anomalies high in the atmosphere that line up suspiciously well with volcanic regions. Changes in radar backscatter over time near big volcanoes, the something changed here signal, and chemistry in the air that looks like it gets fresh inputs. Nobody's selling volcano safaris, but Venus doesn't look retired. Under the surface, the parts list is familiar: iron core, rocky mantle, crust. But unlike Earth, Venus has no global magnetic field. That tells you about the engine. Either the core's convection isn't organized enough, or the planet's slow rotation helps kill the dynamo. Instead, Venus grows an induced magnetosphere when the solar wind slams into its ionosphere, a magnetic bubble by pressure, not by internal generator. It works as a shield in a pinch, but it's not the self-powered force field Earth enjoys. How did Venus end up in the sauna while Earth got the temperate house? The short story is a climate fork taken early and never corrected. Venus probably started with some water, but less than Earth. Being closer to the sun and baked by a tougher early environment, it couldn't keep oceans on the surface. With little liquid water to pull CO2 out of the air and lock it into rocks, the carbon stayed upstairs. More CO2 meant a stronger greenhouse, hotter air, even harder for water to stick around. Over time, sunlight split water vapor, the hydrogen escaped to space, and Venus lost a key climate lever for good. Today, the atmosphere's deuterium to hydrogen ratio is heavily skewed compared with Earth, one of the fingerprints of that long, slow water loss. Earth found a thermostat, oceans, weathering, plate recycling. Venus welded the thermostat to max. Let's talk sound and vision, because they're weird here. On Earth, light scattering by air makes the sky blue. On Venus, the thick CO2 and aerosols turn everything sepia. Shadows are soft, but not friendly. If you clap your hands, sound would carry farther, dense air. But the high frequencies would get eaten fast. Your clap would sound dull and heavy. If you could pick up a rock, it would be hot to the touch, because the ground is oven temperature, and the air conducts heat like a bully. What about the idea of life? On the surface, no. Too hot, too dry, too chemically aggressive. In the clouds around 50 to 60 kilometers, people have speculated about microbes surfing the droplets. It's a neat thought experiment with a long list of problems. Acid for lunch, almost no water, and droplets that evaporate as they fall. Every few years, a new paper throws a spark. Unexplained ultraviolet absorbers in the clouds, odd chemistry that refuses to behave. The honest take? Intriguing puzzles, not evidence. If anything surprises us, it will be at that temperate altitude, and it will have to survive in an environment that hates gear, let alone cells. Back to the weather engine. Why does the atmosphere run laps so fast? The full answer is a grumpy stack of equations, but the elevator pitch is strong solar heating at the cloud tops, huge planetary scale waves, and momentum moved downward from those fast upper winds. Venus is a slow spinner. The atmosphere makes up the difference aloft. You can watch big standing waves parked over highlands, Aphrodite Terra's mountain scale wave trains like wind-formed banners that refuse to budge. Down low, the air crawls, but remember, crawl times 92 bars equals shove. Let's ground this with what we've actually touched. The Soviet Venera landers hit the surface in the 1970s and 80s and survived for dozens of minutes to a couple of hours each. They sent back the only photos from the ground: orange light, blocky basalt, a flat horizon, and the feel of a place that wants your electronics to cry. The Vega balloons floated in the clouds, proving we can sail that altitude band. Magellan's radar maps are still the atlas. Venus Express and Akatsuki gave the atmosphere a long stare and found behavior that demands another round of questions. The next wave, DAVINCI, a probe that will dive through the atmosphere and image tesserae terrain during descent. VERITAS, a high-resolution radar mapper with topography and gravity to match. And EnVision, ESA's orbiter with deep subsurface and atmospheric instruments, is built to answer the practical stuff. What are tesserae made of? Where is active volcanism happening now? How does the atmosphere breathe from top to bottom? And what's making those UV patterns? Dates slip. Space is hard. The questions aren't going anywhere. Observing from home is the dessert course. Venus is so bright, it'll cast shadows under dark skies. Watch it swell into a big, thin crescent near inferior conjunction and shrink to a small gibbous when it's on the far side of the sun. If you're imaging, try UV filters. They pull texture from the cloud tops you can't see in visible light. And if a transit of Venus ever returns in your lifetime, it won't for most of us, treat it like a once-in-a-century eclipse. Safe solar filters, cleared schedule, bragging rights for decades. Why does Venus deserve a longer script than Mercury? Because it's the closest controlled experiment we have for Earth-sized planet, different settings. Same scale, different rotation, different water story, different climate outcome. It's a mirror with a warning label. Size alone doesn't save you. What matters is the system, water, carbon, rock, sunlight, and time, and how those pieces pass the baton. Earth found a way to swap heat and carbon between air, ocean, and mantle. Venus didn't. That's not a morality play. It's a blueprint. So when you see Venus blazing low in the twilight, remember what's behind that elegance. Acid clouds sprinting around the planet, a surface hot enough to soften lead, plains poured by old fire, hills made by a crust that lifts and cracks instead of sliding, a clock that runs backward, and just enough mystery in the clouds to keep sober scientists arguing in very polite voices. Beautiful from here, brutal down there, and scientifically, the best bad neighbor you could ask for. Picture Venus's atmosphere like a stack of blankets that never cools off. Earth has one comfy blanket, thick enough to keep nights from freezing, thin enough to let heat leak back out. Venus piled on 90 more, all made of carbon dioxide, then misted the top blanket with sulfuric acid for flare. Sunlight gets in easily, the ground heats up, and the heat can't escape. That's the greenhouse, no metaphor needed. If Earth is a warm bedroom, Venus is a self-cleaning oven that forgot to turn off. A quick floor-by-floor tour helps. At the very top, around 70 kilometers up, the cloud tops are bright and fast. The air up here sprints around the planet in about 4 Earth days. Think of the planet as a lazy turntable and the atmosphere as a conveyor belt that someone set to ridiculous. You see huge ripples in the cloud deck, like corduroy made of vapor, and over each pole the winds curl into a double-eyed whirlpool big enough to swallow a continent. Drop to 50, 60 kilometers, and it's the maybe we can float a robot here zone. Temperatures are in the roomish range. Pressures are like an airplane cabin, and the sunlight has turned a warm amber. It sounds friendly till you remember the clouds are sulfuric acid and the air is almost pure CO2. Fine for steel and sensors, not for lungs. Keep descending, and the air gets so thick you could almost lean on it. Near the ground, the wind is slow, but it pushes like a heavyweight. Dense air does that. The light turns to a permanent orange afternoon. It's not dark. It's filtered. On a good day, you'd see a flat volcanic plain, scattered rocks, and low rises, with the horizon a bit closer than on Earth because Venus is slightly smaller. There's no rain that reaches the ground. Acid droplets form up high, fall a bit, and then evaporate in the hotter layers below. Vega, but meaner. The result is a surface baked to around 465 degrees Celsius and bone dry. If you could pick up a rock, it would be hot simply because everything is. Under that orange sky, the ground tells a story you can read without a geology degree. Most of Venus is broad basalt plains poured out by ancient volcanism. Picture a planet-sized pancake griddle. Across those plains you find the planet's signature weirdos. Coronae are huge rings of fractures, like someone pressed a hot cookie cutter into softened crust. Upwelling heat domes the surface. It cracks, then relaxes and sags. Tesserae look like a tile floor someone folded and refolded until it wrinkled old crisscrossed uplands that probably preserve the planet's toughest, most complicated crust. There are pancake domes. Yes, that's what they look like. And lava channels that run for hundreds of kilometers, smoothed and stretched by the thick air and the lava's chemistry. Earth has its own lava artistry, but Venus went bigger and tidier. Is any of this still active? The boring but honest answer, probably, at least in spots. We've seen suspicious changes in radar reflections over time near volcanic features, like taking 2 photos years apart and noticing something's different. We've measured heat-related hints aloft over known volcanic regions. And the air does chemistry that makes more sense if fresh gases bubble up sometimes. No one's found a live lava fountain, but the stove doesn't look cold. Inside, the parts list is familiar: iron core, rocky mantle, rocky crust. But the engine light, tells a different story. Earth's magnetic field is powered by a churning, conducting outer core. It's a planetary dynamo. Venus has no global field. That doesn't mean space ignores it. When the solar wind hits, Venus grows a magnetic bubble by brute force, like wind shaping a flag. But there's no self-powered shield. Why? Slow rotation and the way heat moves inside probably keep the core's motion too disorganized to run a clean generator. Think of Earth's core as a well-tuned bike dynamo, and Venus's as a fan that never quite spins fast or steady enough to light the bulb. The water story is the heartbreaker. Venus likely started with some water, not oceans like ours, but enough to matter. Closer to the sun and baked harder early on, it struggled to keep that water at the surface. With little liquid water to scrub CO2 out of the air and lock it into rocks, the carbon stayed aloft. More CO2 warmed the planet, which made it even harder for water to hang around. Sunlight split the water vapor, the light hydrogen escaped to space, leaving behind a higher deuterium to hydrogen ratio. That's the forensic clue in the air today. Earth found a thermostat with oceans, rock weathering, and plate tectonics. Venus welded the thermostat to high and lost the wrench. Speaking of plates, Earth's crust is a jigsaw puzzle in motion. It dives, collides, recycles, and vents heat steadily. Venus looks more like a solid lid. No global system of sliding plates. Heat builds under the lid and escapes in bursts. Big floods of lava, broad uplifts, cracking fits that make coronae and rifts. It's the difference between simmering a pot with the lid tilted, Earth, and clamping the lid on tight, Venus. One is messy but stable. The other is quiet. Until it isn't. If you want a pocket guide explanation of the super-rotation, the atmosphere's sprint, use this. The sun heats the cloud tops unevenly. Planetary scale waves pick up that push, and the thin whiff of friction from the surface can't reel the upper winds back in because the ground barely moves. Momentum piles up aloft. The result is a world where the air laps the rock. If that feels backward, it is. Welcome to Venus. What would it sound like down there? Dense air carries sound farther, but it muffles the high notes. Your voice would travel like you're talking through a warm scarf, low and dull. Clap your hands, and the sharp crack turns into a thump. And because sound moves faster in CO2 at those temperatures and pressures, everything would feel a bit off timing, like the room is messing with your ears. Life? On the surface, no. Too hot, too dry, too aggressive. In the cloud layer, around 50 to 60 kilometers up, people float the idea of tiny microbes hitchhiking on droplets. It's a fun thought experiment with a long list of problems. Almost no water, acid for breakfast, and droplets that don't last. Some odd ultraviolet patterns in the clouds keep the debate alive, but the right summary is interesting chemistry, not evidence of critters. If we ever find anything, it will be because we sent instruments into that altitude band and they got very lucky. How do we actually know these things? Because tough hardware went and looked. The Soviet Venera landers touched the ground, took photos in that orange gloom, and lasted minutes to an hour or two before the planet won. Balloons floated in the cloud deck and rode the upper winds. An orbiter mapped the whole planet with radar. Other orbiters stared at the clouds for years and watched the weather change. The next wave of missions, one that dives through the atmosphere with cameras and sensors and others that remap the surface with sharper radar and peaks below the top layer, should tell us what tesserae are really made of, where the heat is coming out today, and how the atmosphere breathes from top to bottom. Space schedules slide. That's life. The questions are patient. Bringing it back to Earth keeps it simple. Air. We breathe ours. Venus's would melt your parachute. Heat. We vary with season and latitude. Venus cooks everywhere all the time. Magnetism. We have a built-in shield. Venus borrows one from the solar wind. Tectonics. We run plates. Venus wears a lid. Day. Ours is 24 hours. On Venus, the sun bumbles across the sky over 117 Earth days, and the whole scene runs backward. Water. We swim. Venus keeps a forensic whiff and a scar in its hydrogen ratios. Moons. We have one. Venus has none. Not every difference has a lesson, but together they explain why two almost twins grew up to live very different lives. And still, from here, Venus is gorgeous. It's the brightest planet in our sky, throwing off a glare so strong it can cast a faint shadow on a really good night. Watch it swell into a thin, elegant crescent through a small telescope, and you'll understand why people used to track it with nothing but eyes and patience. The beauty is real. So is the physics under it. Acid clouds sprinting, a heat engine locked on high, a surface that looks calm because the weather stops at the ceiling, and a crust that creaks by lifting and cracking instead of sliding. Venus is not evil Earth. It's Earth's sibling who took the other path and followed it all the way. If you want to see Venus yourself, think twilight, not midnight. It never wanders far from the sun in our sky, so you catch it low over the horizon when the day is ending or just beginning. In the evening, look to the west after sunset. In the morning, look to the east before sunrise. A clear, flat horizon helps. A beach works. A rooftop works. A prairie works. To the naked eye, it's a brutal spotlight. Through binoculars, it becomes a tiny disk. In a small telescope, you'll see phases from a thin, elegant crescent to a chubby gibbous. If you're into imaging, an ultraviolet filter can tease out patterns in the cloud tops that visible light hides. And yes, say the obvious safety line out loud. Don't sweep near the sun with optics unless you're using proper solar filters and you know exactly what you're doing. Eyes are not replaceable. A few persistent myths need retiring. Venus isn't a star. It's Venus, the brightest planet, just very good at reflecting sunlight. It isn't hot simply because it's closer to the sun. It's hot because the air is almost pure carbon dioxide and 90 times thicker than ours. Think of Earth's atmosphere as one nice down comforter. Venus stacked 90 heavy wool blankets on top and then misted the top layer with sulfuric acid for flavor. Sunlight gets in, the ground heats up, and the heat can't get out. That's the greenhouse. No metaphor is required. Clouds don't mean rain either. On Venus, acid droplets form high up, start to fall, and then evaporate long before they reach the ground. It's rain that never gets home. And the backward spin? Unusual, sure, but not magic. Venus rotates so slowly and in the opposite direction to most planets that the sun rises in the west and sets in the east. Finally, no global magnetic field doesn't mean space ignores the planet. When the solar wind hits, Venus grows a magnetic bubble by brute force. It's a windsock, not a built-in shield. Useful in a pinch, not deluxe. Why do scientists care so much about this place? Because Venus is the cleanest control experiment we have for Earth-sized planet. Different settings. The two worlds are almost the same size, but Venus spins slowly, keeps almost no water, wears a carbon dioxide sky, and runs geology under a stiff, stagnant lid instead of moving plates. That lets us test ideas without getting tangled in size differences. Climate is the headliner. Venus shows what happens when carbon stays in the air and water can't run the thermostat. Geology is the second act. Without plate tectonics, heat builds up under the crust and escapes in bursts, broad uplifts, cracks, lava floods, and those weird circular features called coronae. For exoplanets, Venus is the cheat sheet. Telescopes keep finding hot, close-in rocky worlds that look like super Venuses. Understanding ours makes theirs easier. And the atmosphere is a wind tunnel the size of a planet. The top deck laps the globe in about 4 Earth days. Polar vortices spin like giant whirlpools, and gravity waves march across the clouds like ripples on corduroy. Even the water story matters. The air carries a forensic clue, a heavy deuterium to hydrogen ratio that tells us most of the original water was split by sunlight and the hydrogen escaped to space. The next probes are built to stop the guessing. One mission will drop a smart sensor package straight through the atmosphere and take a chemical profile from top to bottom while snapping images of the rugged tesserae terrain on the way down. Another will map the surface with sharper radar, measure the shape of the ground, and track subtle changes over time, exactly the kind of data that can catch a volcano in the act. A third will do the deep scan, peeking a little below the surface and watching how the air breathes from orbit. Space schedules slip. Rockets are dramatic. The goals are steady. Better maps, better chemistry, better timelines, and fewer hand-wavy sentences when we explain what's going on. If the greenhouse still feels abstract, here's the 3-step version you can say without notes. Step 1. Start with earthish ingredients, rock, metal, some water, some carbon dioxide, but put the world a bit closer to the sun. Step 2. Without oceans to scrub carbon dioxide out of the air and lock it into rocks, more CO2 stays upstairs. The air gets warmer. Water struggles even more. Sunlight splits the water vapor, and the light hydrogen leaks away to space. Step 3. And with the water lever broken, the system settles into hot and thick. The crust doesn't run plates. The lid stays on, heat vents in episodes, the clouds race, the ground bakes. That's it. Analogies help the rest slide into place. Earth's tectonics are a simmering pot with the lid ajar. Steam escapes steadily. Venus is a sealed pressure cooker, quiet until a big vent, then back to quiet. Earth's jet streams are highways in the sky. Venus is the Autobahn. The top deck laps the planet, the ground crawls, but in soup, Earth has a built-in magnetic generator. Venus holds up a windsock and lets the solar wind shape a bubble. Earth's water is plumbing, oceans, rivers, rain. Venus has ghost pipes, acid mist that evaporates mid-fall, and a faint chemical scar in the air that says, "I once had more." A few quick questions always come up, so fold the answers into your narration. Could people ever go there? Not to the surface. It's an instant regret zone that cooks hardware in minutes. Floating labs around 50 to 60 kilometers up are technically possible. The temperatures and pressures there are manageable. The chemistry is not friendly. Is Venus active right now? The honest answer is likely in places. We've seen hints in heat signatures and in radar images that change over years near volcanic regions. Why no moon? Orbital history No big lucky impact at the right time and place, and nothing stuck later. Why does the sun rise in the west? Because the planet spins backward. Do the clouds ever show patterns we can see from Earth? In ultraviolet, yes. With the right filter, dark and bright swaths in the cloud tops pop into view. If you were a probe, your descent would feel like this. You start above the clouds, where the air runs laps around the planet in 4 days and huge ripples roll through the bright deck. As you drop into the top of the cloud layer, the light turns warm and the temperature feels almost normal, but the droplets around you are sulfuric acid, and the air is almost pure carbon dioxide. Deeper still, the air fattens so quickly you can almost lean on it. Heat conducts into everything. The wind near the ground is slow, but dense air pushes like a moving wall. Touchdown is orange gloom, basalt rubble, and a horizon that looks slightly bent because the thick air bends the light. Your microphones hear a heavy hush. Sharp sounds turn dull. If you last longer than an hour, you were over-engineered and lucky. Venus always wins. Now, rewind and compare Venus to home in one clear paragraph so the differences stick. Our air is 1 bar, breathable, and full of water vapor that shuffles heat around. Venus's air is 92 bars, mostly carbon dioxide, with cloud decks of sulfuric acid and almost no water at all. Our temperatures swing with seasons and latitude. Venus sits at about 465 degrees Celsius, pretty much everywhere, day and night. We spin once in 24 hours in the normal direction. Venus takes roughly 117 Earth days for a solar day and runs the clock backward. We move plates. Venus wears a lid and vents heat by lifting, cracking, and flooding lava across broad regions. We have a strong magnetic field built by a churning core. Venus has no global dynamo and borrows a magnetic bubble from the solar wind. We swim. Venus keeps only a forensic whiff of water in its air. We have one moon. Venus has none. Same size, wildly different outcomes. Bring it home with a clean recap you can deliver in one breath. Venus is Earth-sized, but not Earth-like. A world wrapped in a carbon dioxide sky 90 times thicker than ours, topped with acid clouds that sprint around the globe in 4 days, and a surface that sits at oven temperature under a crust that lifts and cracks instead of sliding. It spins backward so slowly the sun rises in the west, probably still leaks heat through volcanism here and there, lacks a built-in magnetic field, and carries only a chemical trace of the water it started with. It's gorgeous from here, brutal down there, and the best reminder that size doesn't set a planet's fate, systems do. Let's round out Venus by walking the map, then the sky, then the mysteries that still refuse to sit quietly. Start with the ground. If you could fly a slow drone over the surface, you'd drift across enormous basalt plains that look like a planet-sized parking lot poured in dark stone. In the north, you'd see Ishtar Terra, a highland the size of Australia, with Maxwell Montes poking up like a dented knuckle. It's the tallest mountain on Venus. But even there, the air sits on you like a stack of mattresses, and the light stays a permanent orange afternoon. Slide toward the equator, and Aphrodite Terra sprawls beneath you, long rifts, cracked plateaus, and the kind of broad uplift you get when a planet vents heat without moving plates. Here and there, pancake domes squat like perfectly poured batter that refuse to drip. Nearby, A sinuous channel runs arrows straight for hundreds of kilometers as if a river once carved it. It wasn't water. It was lava, kept running by heat and helped along by that thick, suffocating air. Every so often you pass a corona, a gigantic ring of fractures and ridges, and you can almost feel the motion that made it. Hot rock rising under a stiff lid, the crust bulging, cracking, and then relaxing like bread that rose too fast. Over the oldest uplands, the tesserae, the ground looks like a crumpled sheet of foil. The crossing ridges and troughs are messy, which is exactly the point. This terrain is old and stubborn. It kept its scars when the rest of the planet got resurfaced. Now climb back into the air and take the descent one more time, but slower. At 70 kilometers, sunlight blazes off a smooth white deck of sulfuric acid droplets. The winds up here are absurd, whipping around the planet in about 4 Earth days. If Earth's jet stream is a freeway, this is the Autobahn at rush hour. At 60 kilometers, it feels almost friendly. Temperatures flirt with roomish, pressure isn't terrible, and the light goes warm and peach-colored. This is where engineers daydream about floating labs, pressure balloons that cruise the golden altitude while the instruments chew on the chemistry. Drop another 10 kilometers and friendliness ends? The air fattens quickly. Heat moves through it with the efficiency of a hot skillet. Your gear stops being cool and becomes preheated. By 30 kilometers, the cloud droplets are thinning, the acid is still rude, and the view is turning into haze. Near the ground, the wind hardly moves, but in air this dense, even a gentle shove can topple a tripod. We should talk about lightning because people love lightning. On Venus, it's still an argument. Spacecraft have heard radio snaps that sound like electrical discharges. Optical flashes have been teased out of the glare. The atmosphere certainly has the ingredients for sparks. Thick clouds, dust, turbulence, and the kind of vertical structure that lets charges separate. If you ask me to bet, I'd bet yes, but not the way it happens on Earth. Even Venus's fireworks are on brand familiar shape, unfamiliar settings. There's also the strange business of the unknown ultraviolet absorber. When you look at Venus in UV, dark swaths smear across the clouds like ink in water. Something up there is swallowing light in a very specific way. Is it sulfur chemistry doing something fancy? Dust born from volcanic burps? Complex molecules behaving badly? We don't know. It's the kind of mystery that keeps instrument designers sketching on napkins years after dinner. People always ask about terraforming, so let's cut through the sci-fi fog. Turning Venus into anything like Earth would mean removing most of the atmosphere or locking its carbon into rock, cooling the surface by hundreds of degrees, and somehow convincing the planet to run a new stable water cycle. Each of those steps is a moon-sized lift. Together, they're fantasy with extra steps, floating laboratories at the golden altitude. That's engineering with mean chemistry. Terraforming the whole planet. That's a wish. What Venus still owes us are the basics done properly. We need sharper maps to pick out where the ground changed in recent years, not eons. We need a clean, top-to-bottom chemical profile of the air, with real numbers for trace gases that come and go. We need rock compositions from the oldest crust, because those tell us whether Venus ever flirted with continent-like chemistry or its basalt all the way down. And we need time, years in orbit, because that's how you catch a planet in the act instead of reading only its diary. From home, none of that complexity shows. You look west after sunset or east before sunrise, and there's the show-off, bright enough to cast a faint shadow if the night is dark and you're lucky. Through a small scope, the disk fattens and thins, a perfect lesson in phases. If you could see in ultraviolet, the cloud tops would show texture, bands, and swirls wrapped around the globe by those racing winds. Every now and then, centuries apart, Venus draws a tiny black bead across the sun. We timed those walks to weigh the solar system. That's the charm of this planet. It's beautiful enough to be a beginner's first wow, and complicated enough to keep professionals arguing for lifetimes. So here's the straight summary you can read without gasping. Venus is almost Earth-size, but it runs on a different rule book. The air is 92 bars of carbon dioxide with acid clouds. The ground is oven-hot basalt under a stiff, stagnant lid. The winds up high sprint while the rock below barely turns. The planet may still burp lava in places, but it hides the evidence under haze and heat. It spins backward so slowly the sun rises in the west, has no global magnetic field of its own, and carries a chemical scar that says most of its water left long ago. From our yards, it's the morning star and the evening star. From up close, it's a pressure cooker with a racing sky. Venus looks simple from here, a bright pin of light that shows up on schedule and steals the scene from the stars. Up close, it's the opposite of simple. It's a planet the same size as ours that chose different settings. A CO2 sky stacked 90 blankets deep, acid clouds sprinting laps in 4 days, a crust that vents heat in big, moody episodes instead of sliding around on plates, and a clock that runs backward so slowly the sun rises in the west. None of that is a myth or a metaphor. It's just what happens when water can't keep carbon out of the air, and a rocky world loses the levers that moderate it. That's why Venus matters. It isn't evil Earth. It's the control experiment. Same scale, different system, brutally clear outcome. It shows that size doesn't save you, and distance from the sun isn't the whole story. What saves a planet or cooks it is the full machine: water, rock, carbon, sunlight, and time passing the baton. Venus dropped the baton early and never got it back. We study it because it's honest. It tells us, without flinching, what physics does when the thermostat is welded on high. The good news is we're not guessing in the dark anymore. We've stood on the surface for minutes, floated in the cloud deck, mapped the ground by radar, and watched the wind engine run from orbit. The next probes will dive through the air, remap the crust with sharper eyes, and stop hand-waving about what the rocks are and where the heat is leaking out today. Venus will not get friendlier, but it will get clearer. So keep the ending image simple. You, outside at dusk, watching the evening star burn through the glow. It's beautiful, and it will always be beautiful. Now you also know what's behind the brightness, an oven-hot world with a racing sky, and why scientists keep pointing back to it. Venus is the best bad neighbor. Dazzling to look at, rough to visit, impossible to ignore, and absolutely worth understanding.